In this picture, we can see that we can draw an area of competence like a series of sheets, like working sheets, in which in each area of competence you make all the actions that are needed to produce the decision for the project. So you might identify a group of working sheets related to an area of competence. So there will be the subsystem, let's say, for power, the power subsystem, and there will be a working area with a lot of working sheets in which all decisions on solar cells, batteries, electrical distribution system are made. The decision in terms of how the parts and the assembly of this subsystem are really made. So you reach the level of the decision of the component. And also you have a bunch of supporting analytical tools that helps you in making the right decision for the project. Of course, all the systems should have a data exchange procedure in order to share all this decision and also the information that are related to that. At La Sapienza, we developed since 10 years an educational concurrent design facility based on the model designed by the European Space Agency. As in the picture before, each area of competence is implemented in a group of working sheets that all together are creating a workbook. Each workbook is related by means of a data exchange modulus to all the other areas of competence in which the system design is organized. In each workbook, you have several sheets that have several functions. There is an input sheet in which the area of competence takes all the information coming from the system design and from the design of other subsystems. Then there are some calculation sheets in which you implement your tools in order to be able to make your design decisions, to evaluate your margins, to evaluate your budgets in terms of mass and energy, and probably also link, if this is the case, that are allowed by the system design manager to each and every subsystem. Then, after doing your calculation and after taking good note of all the steps of your process in an administration sheet, you will end up by providing some output sheet in which all your decisions are shared with the other areas of competence. So basically, an environment of concurrent design is made of different areas. Those areas could be implemented in an hardware architecture, like in working position, in which you have around the table several competencies that are related to the mission, to the system, to the configuration overall of the spacecraft, but also to all the areas covering the competencies needed for each subsystem. So you need an hardware architecture, but you also need a software architecture that is able to provide the sharing of all this amount of information. And also there should be a database in which you can find information about parts, about items that you might consider to be present in the market or that you need to develop in order to implement the real assembly of all the spacecraft. In order to do a proper shared design process, you first need to be clear on what are your design variables and what are the decisions that each area of competence should make. So in order to do that, we proceeded to the formalization of the system and subsystem design procedures. So, as described in the picture before, in a concurrent engineering process, each subsystem design node is reading some input, performing a sizing criteria and making the decision for design, and producing output values for design variables. This process flows in a very interactive way, touching all the areas of competences that are involved in the design process. So, a formal and uniform description of the design variables and the interaction of such variables between subsystems is absolutely needed. And we have accomplished that with the help of UML activity and class diagrams in order to formalize such kind of data modeling. We start by describing a mission class diagram. You see at the center of the picture this box that is describing the name of the area of competence. Of the node, if you like, of this multi-node network for the design process. And of course, this area of competence of mission is giving a lot of requirements to all the other areas of competencies, saying, for instance, to the area competent of attitude and orbital control system, what are the requirements in terms of pointing, and maybe telling to the area of competence of structure what is the launcher and the launch system that has been chosen, so that the structure can make their own decision based on the load coming from a certain launcher. The mission is giving some information to the power subsystem to describe the number, the duration of the eclipse, or the number of eclipses per year, in order to allow the electrical system to be designed in the presence of such event of the mission. And we can describe all that for all the other subsystems. Basically, the mission is the starting point from which all the system is being designed. Then we go to the system class diagram, in which at the center of the attention is the system itself. So the area of competence in which all the information from all the other subsystems and from the payload are gathered, and at the same time there are information from the system management to all the subsystems. The first and most important information that the system design area of competence is providing to all the others is the mass budget, saying what is the percentage of the total mass of the satellite that each area, say the payload or the structure or the attitude control system, could actually spend in terms of resource in order to deploy the design of the spacecraft. And there is also a budget for power and a budget for the link for telecommunication, meaning that the system area of competence is making decisions on the management of the very scarce resources that are available on board the satellite. And the most scarce resources are actually the mass of the satellite, because we spend a lot to put a satellite in orbit, and this the amount of mass of the satellite is an important parameter to determine the cost of the satellite itself. Another very scarce resource while operating the satellite is the power, because we don't have the energy available like on ground just by just plugging into the network of electricity. We need to produce power by means of solar cells, and the surface of solar cells is somehow limited. So we have a limited amount of power available. And also, the link budget limits the quantity of information that we can transmit back to our ground segment. So basically, all the information that is coming from the area of competence of system is relevant to such budgets, and also, of course, to all the requirements and the geometry that is needed to implement overall the satellite. So there are information coming and decisions coming from the area of competence of system and going to all the others, to the payload, to the structure, to power, AOCS, propulsion, thermal, and so on. At the same time, after the other areas of competence has completed their decision in terms of project, that are information coming to the system, for instance, the real mass used by each subsystem is a reply to what the system is allowing you to spend, and you might be in the situation of having spent not all the mass budget that the system has assigned to you, or having been able to spend less and to have some margin for your mass. So there is this interaction between the area of competence of system and all the others. But if we go onward, and for instance, if we concentrate on the structure class diagram, meaning the area of competence of the structural subsystem, this diagram is representing the flow of information going to the area of competence of structure, like in the input worksheet of our workbook, and coming out from the area of competence of structure, going to the other areas of competence. Once again, it's very important that this flow of information is nicely described in a very precise manner, so that there is no confusion about what variables are entering in one area and coming out from that area. The definition of this variable should be very well described, and all this information is working in process while all the activity are going on in parallel. After the structure class diagram, we can also evaluate other class diagrams of subsystems. Once this formalization is performed, of course we need to establish some internal criteria from the area of competence viewpoint in order to make the decision of the configuration of your subsystem, the description of the parts of the subsystems, and also the sizing of the subsystems, so that at the end of the design process we can provide to the manufacturing unit all the information that are needed to actually produce, implement, assembly, integrate, and test the satellite system as a whole, as a combination of hardware and software parts that work together for the functionality of the overall system. So basically we can again use the example of the structural subsystem to understand how such working sheets are made and implemented. The first thing that you need to do is to understand which are the parts of your subsystem. We might concentrate on a telecom satellite, and we might identify in a central cylinder kind of geometry for such satellite, the configuration of your subsystem in terms of the geometry of the mechanical assembly and the elements, that is to say, the structural components that are making all the assembly. After describing the overall geometry of the structural elements, for each element you can identify the loading that are coming from the mission, from the transfer of loads and forces and constraint, and then we might define a sizing criteria for each element. We might define a scheme, in this case of loads and constraint, in order to be able to set up a simple way of defining the level of stress or the level of strain that are reached by your component. And of course, when you are evaluating the component, you have already made some decision about the material that is being used, or the thickness of your component, or the way that the component is constrained by the other ones. And all that is implemented in the component sizing calculation sheet. In the example that I'm showing to you, the component to be analyzed is the payload adapter, meaning the element that has the shape of a truncated cone that is placed between the satellite and the launcher, and it's able to provide the satellite the support by the launcher and transmit all the forces producing by the inertial forces while the launcher is providing a certain acceleration to the satellite. So in this diagram you see some information concerning material properties or launcher constraint in terms of mechanical environment provided during launch. There are general missions parameters that are also important. And then there are the geometrical part of your component, and there is a scheme, a mechanical scheme for sizing the material and for sizing the component and evaluating the strength, that is to say the stress that you can calculate by doing some simple calculation. And this is exactly what you are doing with this calculation sheet. So by means of some parameters that are obtained from other areas of competence, then you make your own decision, and you at the end produce information about your the sizing and the material of your mechanical component. You do that for all the mechanical components that are part of the structural subsystem, and then you do the mass budget calculation, in which you calculate all the mass involved in the structural subsystem, so that you see if you are respecting or not the limit that the system area of competence is giving to you, and if you have enough margin for proceeding to the next phases of the project. You can do that for all the subsystem. Of course, the power subsystem would have different criteria, different sizing criteria. The shape and the characteristics of different parts will be really different, but the idea is always the same. You describe the architecture of the subsystem. For each component, you define a simple sizing rule to make decisions on it. You pick the right material, the right component, the right elemental part in order to set up your subsystem in a proper way with the help of some simple tools for sizing. Then you evaluate your budget. Maybe mass is not enough. You have to do also the evaluation of the power budget and the link budget. And then you provide all those decisions as as an output of your activity through the input workbook. So once again, as a summary for describing what a concurrent design facility looks like, there should be an hardware and software architecture in which all the areas of competencies are sharing each other the decisions on the process. In each area there is a workbook of many worksheets in which you have input and output worksheets, but also some calculation worksheet that is internal to each area of competence. And you can share all this information in a simultaneous way, provided the good formalization of the description of the design variables are made, and also the flow of this information and the responsibility on each variable is assigned to a certain area of competence. Also, a database design would enable all the nodes of the system to work together, and of course there will be a major effort in the configuration area of competence in which all those information are also put together to provide a nice geometrical description of the system.